Hi, welcome back. So we're in Chapter 5, Prediction by Probability at the outline bivariate concept of probability. So in real life, we are often interested in several random variables that are related to each other. For example, suppose that we choose a random family and we want to study the number of people in the family, or maybe the household income, the age of the family, etc. And you could see that each of these are actually considered to be random variables. Now, in this particular outline here, the bivariate is going to be only depends on two, but once we understand the two, we can establish that to multivariate concept of probability as well. So let's just start first of all study if our variable is a discrete. These are actually the concept that we have established so far given any kind of distribution we study in the univariate. So this one's saying probability mass function, but it's going to be joined a probability mass function. So let's say I have random variable x and I have random variable y. We would like to study them jointly. We define the joint probability mass function of a discrete random variable. Let me just say what is this range xy. Range of xy is just subset of the range of x multiplied by range of y. The sum of values here of the probability xy is just equal to 1. We can actually from here look at something called the marginal probability mass function, right? The joint probability mass function, this guy here, contains all the information regarding the distribution of x and y. Let's take an example here and try to put this information all together. Now consider two random variables, let's call them x and y, with a joint probability mass function as given in this table. I would like to actually graphically represent this information. I mean, say, this is a graphical representation of that. Let's try to find the probability x is equal to 0 and y less than or equal to 1. What is the range of the x here? Could be 0, 1. A range of y could be 0, 1, or 2. We are looking at a joint probability mass function where x is 0. Well, it's taken only one of the outcome of the range. And y less than or equal to 1. So could be 0, could be 1. I can rewrite this. 0 and 0 is 1, 6. Plus 0, 1 is 1, 4. Which is equal to 5, 12. What is the marginal probability mass function of x and y? Since we defined the two ranges of x and y, these are the range of x, right? We get the 0, we get the 1. Let's look at the 0 first, and then you will understand the concept afterwards. Px of y of 0 and 0 plus px y 0 and 1 plus px y of 0 and 2. And if you substitute the value 1, 6, 1, 4, and 1, 8, 13 over 24. This is only a probability of x of 0. We can do the same for 1. So what we can end up with is that we can rewrite like this. Px of x could be 13 over 24. The first one we found, this guy here. When x is 0, 11, 24, when x is 1, it's going to be 0 otherwise. Py of y was the same concept. These are the probability mass function we call the marginal, actually. I think it's time now to join second important part, which we were talking about, is the cumulative distribution function. So we're going to call it a joined cumulative distribution function, which is equal to the probability of x to be actually less than or equal to some value of x. Well, it's the same thing when we take the joint here of x and y. But let's talk about something, if you remember, called the conditioning and independency. Just let me actually remind you with the general formula of that probability of A given B is just equal to the probability of A intercept B over the probability of B. When, of course, you have to make the condition clear, probability of B larger than 0. We don't want this term to be 0 anyway. Any other formula regarding conditional probability can be derived actually from this exact formula without any changes. So we're going to talk about the joined conditional probability. Let's say that the probability x given event A of x is just equal to the probability of x is equal to that value of xi given the event A over the probability of A. Example will be quite a bit useful. A fair die, and let's x here represent the observed number. What we are trying to find the conditional probability mass function of x, the observed number to be less than 5. We condition on the event A. So what is the event A? That x less than 5. Probability of A, well, it could have been 1, 2, 3, or 4. 4 over 6. So we want to find out whether the outcome happens to be 1. Okay, let's rewrite this particular problem in the form that we've just defined. Probability of x is equal 1, that is 1 in 4. Or multiply by this guy here, its probability is 4 over 6. Divided by 4 over 6, you left 1 over 4. And you will find that actually 2 and 3 will have the exact same probability. How about 5 and 6? Well, it will be 0. Now, from here also we can develop one more concept of the joint. We call it conditional probability mass function of x given y, the value of another variable. So the previous one was talking about event, like this case, event of A. But here we're talking about given y. Let's define it. The probability of x given y, probability of x equal xi, y equal yj, divided by the probability of y equal to yj. This is the exact same term anyway. Just to remind you, actually, you should also remember that term talking about the independence random variable. We have defined two discrete random variables, x and y, are independent if the product of this is equal exactly to the product of their joint. That means we call them, they are independent. And the same thing is applied when you have the cumulative distribution function. So it is the same exact concept. I hope you still remember that from our previous discussion. Now, the last thing maybe we need just to remind you with is to discuss the conditional expectation. Expectation, it means as we target actually from the beginning here, the expected value of x and the variance of x. So basically, I could say that the expected value of x given event A is equal to the sum of xi multiplied by the probability mass function, actually, PDF of that, xi. Xi should be in the range of x. When we did it in a univariate, we were actually taking the sum xi multiplied by the probability mass function, or the f of x, if you remember. Now, from a conditional, given that there's an event A, the expected value is the same. We take xi, the sum of course, multiplied by its probability of x given A. How about if we are given not event A, but y? What is the expected value here? Well, it's the same concept. Well, when it comes to conditional variance, nothing should be different. That is the actual conditional variance. Well, that was all concerning the bivariate probability, given that the variable is discrete. We can also establish the same thing given the variable is continuous. So what exactly we are going to accomplish at the moment, we're going to find something called the joint distribution of these two continuous random variables, f of x and y, such that important conditions should be larger than or equal to 0 for any x and y are in the R. First condition. The second one, in the case of a discrete value, we always dealt with the summation. But since we are looking at a continuous kind of case, so here is where the integrals is going to take place, as we established earlier on. But here we've got joined, so we are not dealing now with one integrals, but actually double integrals. So in this case, what we want double integrals from minus infinity to infinity, and that's where we're going to take the f of xy in terms of x and then in terms of y. And we have to know that the total area of taking this integral, as usual, is going to be 1. Let's take the cumulative distributive function, which is this guy here. It just equals the probability, as we always say, of x to be less than or equal to a, and also y to be less than or equal to the value of b, usually is written as y anyway. That's going to be the f of xy, okay, dx dy. Take the derivative of this, which is going to lead me back to the PDF. I hope this connection is quite clear to you and you make sense out of it. What we can actually establish from there, something related to the marginal PDF. What do I mean with the marginal PDFs? It's a marginal probability density function defined as in terms of integrating out one of the random variables. You could say, well, this is the fx of x. Take the integral minus infinity to infinity, again, the PDF of this joint distribution. But this time we're going to integrate this in terms of the dy. This is if we want to find the PDF of the x. And the same thing, actually, you could look at it in terms of the y thing. So the concept is in there, and I hope that you are clear about it. It's not like something magical to do. Let's look at a small exercise here. Let's take x and y to be drawn as a uniformly. Should looks like that. So you get these points in these two plane terms of x and y. What we want to find from here, actually, what is the PDF of this in terms of x and y? Okay, this is exactly what we want to find. The joint density is constant in this case. Actually, looking at the graph, it's a triangle, right? This is a constant line. It's a kind of a linear. So f of the xy is just equal to some constant for, see, the boundary of the x here to be larger than or equal to 0, and also y in this case larger than or equal to 0, and that the x plus the y should be less than or equal to 3, which is actually the function of this line that we have here. And it's going to be, of course, 0 otherwise. Let's try to find this kind of a substitute for this integrals without looking at this, without looking at the area here. One thing I know for sure, that the area of this guy here, what's the area of a triangle usually? We know half base multiplied by the height. This is a constant, right? So you take the constant out, just take the integrals of that, c multiplied by 9/2. This is the area of the triangle. All this should be equal to 1, as we established earlier on. Is going to be equal nothing but 2/9. Let's now actually take a practical example to cover all what we have been talking about so far. The alpha of xy that we established so far from this example looks like 2/9 for... What we want to find here, we want to find the probability of x to be less than y. Well, from this line, when x is going to be less than y, this area here is actually covered. X is going to be less than y. Let's define the region first. So the probability of x to be less than y is just going to be the double integrals, taking this region C here, and then we have the fxy dx dy. Now let's defining these integrals. Let's see whether we want to work with the x dy, or maybe we can shift actually dy dx. I would like to do it other way around there. So let's start dy and then going to do dx. Why? Because x region, the outer, it's quite a bit easy to define. So every point x is going to cover up to here. So what is this point? It is obvious. It's going to be 3/2. What is the y pi? Well, the values of y, it's going to be actually bounded with this line here up to this line here. What is this line? Well, this line is just x is equal to y. And what is this line? This is going to be 3 minus x. And of course, we know that we are integrating 2/9. So if you do the integrals and everything, you will reach out to the final result, which is going to be equal to half. Now, finally, actually, we can be looking at the multivariate concept of probability. That's exactly what we're going to do next. I will see you then.